Hopefully you're watching these sequentially, and we've just talked about colligative properties and the different particles. And we're coming back to colligative properties. Colligative properties means the number of particles that in a solution that will affect the property. First one we're talking about is Raoult's law. And Raoult's law says that the vapor pressure of a solution is equal to the mole fraction of the solvent times what the vapor pressure is normally for the solution. So for instance, what's the vapor pressure of a solution that's water that's 25 degrees Celsius that has 99.5 grams of sucrose in it and 300 milliliters of water? So vapor pressure of sucrose, I'm sorry, vapor pressure of pure water, 25 degrees Celsius, is 23.8 torr millimeters of mercury. So torr and millimeters of mercury are the same thing. But Raoult's law, so we have to figure out the vapor pressure, we have to figure out what the mole fraction is. So, the new pressure is the mole fraction. The mole fraction is water. So we have 300 milliliters of water, which means we have 300 grams of water. So then the mole's water is mole water to 18 grams water divided by the moles of water so that plus the moles of sucrose. So we have 99.5 grams sucrose times mole sucrose over 342 grams of sucrose. And then this is all times 23.8 torr. And you throw that in your calculator and you get 23.4 torr. So not that much of a change. But the vapor pressure does go down a little bit by about 0.4 torr. So, but that's Raoult's law. Okay, let's talk about the different types of cases with Raoult's law. And we have two solutions, A and B. And the idea is that we have A and B mixed together that and just by mole fraction. So first one here, this is the ideal case. So the y-axis is the vapor pressure, the x-axis is the partial pressure of component A. And so if you look here on the far left, we have no A, and we have all B, and then the solution's vapor pressure is exactly that of B. And then on the far right, we have all of A, no of B, and the vapor pressure is just that between them. And you can see that the vapor pressure solution is just a straight line connecting these 2 points. And that's the ideal behavior. Now, what happens if the solvent and solute are strongly bound? What happens is there's an attraction for them, so actually the solution has a lower vapor pressure. And this line was usually a straight line. It bows downward. And what if there is repulsion? Let's say they don't like each other. And if that happens, then you get that it bows the other way. It bows up. And this also is a phenomenon that explains a phenomenon called steam distillation. So you can take two immiscible liquids and you can get them to boil at a lower temperature. So if you can do this at your home if you want. You can take olive oil and mix it in water. So say you're making like noodles or something like that, and you put in some olive oil into the water. Actually, that mixture boils at a lower, if you're at sea level, it'd be 100 degrees Celsius. It boils at a slightly lower temperature. And that causes that oil to leave, and that creates a phenomenon, like I said, called steam distillation. And problem for this is that if you ever gone to a restaurant and you say, this is a greasy fast food restaurant, or this is a greasy truck stop, because you go there and there's literally grease on things. Like, where did this grease on things come from? It came from the steam distillation. They're cooking with some of the fatty compounds, and the fatty compounds in boiling water will leave, and they'll condense back down onto the furniture, and it's greasy. So you were in fact in a greasy place, and that phenomenon is called steam distillation of how that happens. Okay, if you recall talking about phase diagrams, so if you remember from the previous semester, here's a phase diagram, and well, this one is not water. Water goes this way, but the other three states we have solid, liquid, and gas. I guess it wasn't last semester. It was this semester. Oh no, I guess yeah. But anyways, phase diagram, and the y-axis is pressure, x-axis is temperature, and then we have the liquid phase here. If you add, if you have a solution, the liquid phase actually extends a little. You have freezing point depression, and you have boiling point elevation. So there's a little bit more liquid than there normally is. And if you ever live somewhere cold, you might notice what they do if it's cold and it snows and you want to get rid of the snow on the road. One of the ways you can do is you can put salt on the roads, and the salt will melt the ice or snow. And we'll do a calculation there. So it's the same thing. We have the change in freezing point is the molality. So remember, moles per kilogram times the Kf, the constant, the freezing point depression constant. And then you have the Kb, that's the boiling point elevation constant. And remember, freezing point depression, I'm depressed, I'm down. Freezing point depresses it makes the freezing point go down. And then elevation, I'm elevated, I'm happy, I'm up, I'm high. Elevation makes it go up. So freezing point elevation. Boiling point elevation, freezing point depression. So if you think about freezing point depression, boiling point elevation goes up. All right, so let's do this. So what is the freezing point of a 1.7 molal aqueous ethylene glycol solution? So the freezing, the Kf for water is 1.86, and you have the delta Tf is molal times Kf, so 1.7 times 1.86, and what is that? This is 3.2 degrees Celsius. So now, the next thing you have to do, though, is freezing point depression. Water normally freezes at 0 degrees, 0 minus 3.2. This is minus 3.2 degrees Celsius. So don't forget this step. Don't calculate this, say, oh, it's 3.2, and move on. Don't forget you have to subtract it from the freezing point. And that is, believe it or not, that's the most common mistake that students make, because they forget to subtract it. They figure out the delta TF, but then they don't subtract it from the freezing point. So what? Why do we care? This has to do with hibernation. So we are studying hibernation for a couple reasons. One is for space travel. So why do we have to go to Mars and have to be awake for a year to travel to Mars? Wouldn't it be better if they just hibernated and I woke up and I was fine? So we're looking to hibernate humans. Bears can do it. Bears can hibernate, and the hibernation is unique because when bears hibernate and they wake up with all their muscle tone and their bone mass. For humans, if you put a human in a coma and the human wakes up a couple months later, the human loses a bunch of bone density and muscle mass while he or she is in a coma, right? So there's a clear marked difference between sleep, coma, and hibernation. So, but how some frogs do it, so right as they're about to freeze, so as they're getting close to freezing, then their adrenal glands release a bunch of sugar, then it acts like antifreeze, and then their blood and cells don't freeze. They don't, and a problem with freezing, water expands when it's frozen, so that can cause significant cellular damage if you actually have frozen water in your body. So these frogs, right as they're about ready to freeze, they go into a fight or flight response, and sugar gets released in their bloodstream, and that acts like as an antifreeze. And they're also cold blood, so they just kind of sit there, and then they get cool. And then when spring comes and warms up, then they hop away when their bodies warm up from the melt, and hopefully it doesn't get cold enough that they freeze. So I told you, well, that's a different type of hibernation. I don't know if we're pursuing this in humans or not. We're certainly looking at hibernation like bears do. The other reason why we're also looking at this is that humans don't have a lot of what's called brown fat. We have a lot of white fat. So if you're fat, you're full of white fat, at least for humans. Brown fat is burned. We have some. We don't have as much as bears do. Bears burn fat to stay warm. So humans, I guess if you wanted to lose weight, you could turn your white fat into brown fat and then stick someone in the freezer. So, all right, why don't you go hang out here in this cold area? Why don't you move to Wisconsin and lose a few pounds, kind of thing. Because whenever I go to Wisconsin, I tend to gain weight anyways. So, be a good new diet loss. So, okay. But that's an application, for at least for the freezing point depression. And I'm not going to do boiling point elevation. It's the same thing, but you add it for boiling point elevation. And so let me move on here. This is my picture of a tree. So a tree actually acts like a water pump. So the trees have the roots down in the ground, and then the roots are able to draw the water up to the leaves in the tree. And how does that work? It works by something called osmotic pressure. So how does osmotic pressure work? You probably know that that's how trees work, how root systems work, but it works by osmotic pressure. And we've done this before. The osmotic pressure, the way that we measure it, we use this and we call this a U-tube apparatus. I bet you can never guess why we call it a U-tube apparatus. If you're not following me, it's in the shape of a U. And you have a U-tube apparatus, and you put a semi-permeable membrane, one that water can pass. And if you add solute, what happens is one end gets higher than the other. And so 33 feet of water or 10 meters of water is the same thing as an atmosphere. So if you measure this height of the solution, it'll tell you, you can figure out what the pressure is. And this pressure that goes this way, that pressure is known as the osmotic pressure. And just like the ideal gas law, PV equals nRT. So you can divide both sides by volume. You get P equals N over V RT. N over V is moles per liter. So it's just the ideal gas law. And we use the equation pi, capital Pi equals MRT. Capital Pi is the osmotic pressure. M is molarity in moles per liter. R is a gas constant. T is temperature, absolute temperature in Kelvin. And pi, be careful though, capital Pi can mean a geometric series. So for instance, pi n equals 110, that is this geometric series. And there's also a Raman sum series, that's the adding together. So be careful about all these terms, they mean different things in different classes. But in chemistry class, capital Pi means osmotic pressure. So let's do this. Osmotic pressure. The osmotic pressure of a solution containing 5.87 milligrams of unknown protein per 10 milliliters is 2.54 torr at 25 degrees Celsius. So what is the molar mass of the unknown protein? So this is a little outdated. We tend not to do this anymore. Right now we do usually use what's called an electrospray source and use a time of flight mass spectrometer to figure out protein masses. So we typically don't use this technique anymore. But this is an old way you could do it. I want to do this derivation here. So pi equals MRT. I already talked about that. Capital M equals moles per liter, and moles is your grams divided by the molecular weight. So what you can do is you can take capital M moles per liter and substitute that by grams divided by molecular weight over liters. So, and then you can rearrange that and solve for the equation. So your molecular weight is your grams per liter times the gas law constant R times the temperature divided by the osmotic pressure. So let's go ahead and put it in here. Your molecular weight. This is going to be the grams. It'll be 5.87 milligrams times, so a gram per 1,000 milligrams. So we're going to have it be grams per mole. So, and then this divided by liters, and we have 10 milliliters, so 10 milliliters times liters per 1,000 milliliters. Then R is going to be 0.08206 liter atmosphere over mole Kelvin. Temperature 25 degrees is 298 Kelvin. And then over osmotic pressure, we have 2.45 torr times an atmosphere over 760 torr. So you have to throw that whole thing in your calculator, and in doing so, you get 4.45 times 10 to the third grams per mole. So that's a big molecule, right? Water is 18 grams per mole, and this is 4,450 grams per mole. So it lets you know some things about proteins. Proteins are huge. Proteins are big molecules, and they're made of amino acids. So you can learn about that more if you take biology or biochemistry. And they're big molecules. And so this is always too big for me to comprehend. I'm so much a physical scientist. I'm not really I can't really handle biological things because they're too big. Molecules are too big for me. I'm going to stick to the small ones myself. But that's a protein there. Okay. So this is if you want to try, what is the osmotic pressure of a solution of 1.5 grams ethylene glycol in 50 milliliters of water at 25 degrees Celsius? And that's 11.8 atmospheres. So remember, an atmosphere corresponds to 33 feet or 10 meters. So that's 118 meters. That's over 300 feet, right? So that's how trees. That's how, if you go to see the sequoias in California, you're like, wow, how do these trees get their water all the way up to those leaves at the top of the sequoia? The answer is osmotic pressure, and it's very profound. You can see that they can draw water up very, very high using osmotic pressure. So, all right, the last thing I'm going to talk about is something called the Van Hoff factor. I'm not going to test you on this, but the Van Hoff factor, this is it's a kind of a fudge factor. I know that's a fudge factor. It's like you observe something and you find constants that work to make the semi-empirical, the sort of empirical model work to the data that you're given. So, meaning, and the Van Hoff factor is a way of accounting for the fact that the number of particles seem to be different in the way they act than what they actually are. And if you look at this, for instance, you have sodium and chlorine. So sodium and chlorine in solution, and you have the negative chloride and the positive sodium, and so this is negative, this one's positive. And what can happen is they can kind of hold hands and have an ion pair. And the so what? Well, you have in this case here on the left, this is more like two particles. And when they bind together, this is more like one. And the problem is with colligative properties depend on the number of particles. So since you have these sodium chloride salt, you have the number of moles of particles should be twice as much as you have moles of sodium chloride, but it seems to go a little differently. And like I said, this is the Van Hoff factor, and you can include it in your calculations for that. But I do want to go over this conceptual connection here. Which one of these is going to have the highest boiling point? So we have half a molar of sucrose, half a molar of sodium chloride, half a molar of magnesium chloride. Which one has the highest boiling point? The answer is the MgCl2, because so sucrose here, it's one particle. It's a stable group of atoms. This is one particle. Sodium chloride, this breaks up into Na+, Cl-. Colligative properties deal with the number of particles. There are two particles here. Magnesium chloride, it forms magnesium plus 2 and 2 Cl-. This has 3 particles. Since it's the moles of particles, this is the one. Magnesium chloride is the one that's going to have the highest boiling point, because the boiling point, if you remember, is the colligative property. The boiling point elevation, the delta TB, is equal to the molal, the moles per kilogram, times the boiling point elevation constant Kb. And from this, magnesium chloride is going to have 3 times as many moles of particles as sucrose, for instance. And it'll be a 3-to-2 ratio versus sodium chloride. So, and last thing I'm going to talk about are colloidal dispersions. So, what about other types of solutions? What about things that are not quite solutions? You can get, by entropy, you can get 2 phases of things that kind of mix in a way. And first one is an aerosol. So you get a liquid suspended in a gas. So fog. So clouds, fog. These are water droplets suspended in air. That is called an aerosol, and that's also known as a colloidal dispersion. And what can you use to determine if something is a colloidal dispersion? There's something called the Tyndall effect I'll talk about later. It means scattering of light. You can have solid aerosols, so smoke. Smoke is a solid aerosol. You can have gases dispersed in a liquid. That's like whipped cream. So if you ever make whipped cream, you have to whip it with you have to take heavy whipping cream. You have to whip it for a long freaking time to get it to whip in there. So it's hard. And then you can get emulsions. You can get 2 immiscible liquids together. This is something like milk. So milk is a different suspension of milk fat and water. And then you can get a solid liquid emulsion. So opal, for instance, you have a liquid trapped in a solid. So that is silica. I'm sorry, opal. It's water and silica. And there's I always have to be careful when I talk about this. We have a disagreement about this between chemistry and geology. So geology considers silica to be soluble, so whereas chemistry does not. So generally speaking, if something will not dissolve 5 grams in 100 milliliters of water, that's considered to be insoluble. And by chemistry definition, the silica is definitely considered to be insoluble, but to the geologist's definition, silica is considered soluble in water. So I don't know what their numbers are, but I've got into heated discussions about this with geologists and talked to both students and professors about this, and it turns out we just have different definitions. So interesting how people can get so passionate about this. But with the definition of solubility. Okay, and let me talk about the milk. Well, how do you form this 2 miscible liquids together? You can form it using something called a micelle. If you wonder the way soap works, soap, at least the cationic, most soaps are this way. You have a an anionic surfactant. So, meaning you have a negative end here. So, and then you have the hydrocarbon skeleton. And the way you make, when you have soap, when you put soap on your hands and you have greasy hands, you take the soap on your hands and you run it and you rub your hands together over running water. And the rubbing action, you have to rub your hands together. What that does, that creates these micelles. And you have the oil droplet. So this oil droplet is here in the center of the micelle. And then these hydrocarbon tails, they surround the oil droplet because of like dissolves like. So they will dissolve like, and then the nonpolar heads all go on the outside, and this whole structure is called a micelle. And this kind of looks like something, for the biology folks, it looks kind of like a cell membrane. So a cell membrane, for instance, a cell membrane is called a phospholipid bilayer. What's a phospholipid bilayer? Well, it's actually a phosphate. It's a phosphate group connected to a hydrocarbon. That's a hydrocarbon. So, and there's two of them. So it's a phospholipid bilayer. So your cell membrane is actually 2 molecules thick, and it has a negative charge on the surface. So all biological surfaces are negatively charged because of that. So because of these simple structure here, just 2 molecules thick. Okay, the last thing here is the Tyndall effect. So the Tyndall effect, if you have a beam of light, so you can see that the beam of light creates some scattering here, but not here. That means that this solution here, well, it's not a solution, it's actually a dispersion. So it's a colloid. It's not a solution. This one here, that's a solution. There's no scattering of light. And when you see things like sunbeams, what you're seeing is the Tyndall effect. You're seeing the solid aerosol, and those are the sunbeams. And and here's a picture of the micelle, and this could be like soapy water there. That could be that dispersion. Okay, so we will stop here. On the next chapter.